Hey, hi everyone. Very good evening. Hey, Harsh, good evening. So, is my voice is clear to everyone? Hi, Sosh. All right. Fine then. So let's get started. So before we get into today's topic, what are the things we discussed in yesterday's session? Can you all do a recap on it? What are the topics we have covered in yesterday's session? So Astosh, regression classification, yes. So Harsh, supervised learning, unsupervised learning, classification, clustering, regression, right? So why machine learning? Why we have to get into machine learning? Why machine learning? Can you all post it on the chat box? William, Arti, Galton, Sonia, Rishikesh, Amar, Priyanka, Supriya, everyone. Vidyasagar, Deepan, Renuka, Basim. To make predictions. All right. So okay, I think Harsh has already responded. What is the difference between supervised learning and unsupervised way of learning? What is the difference between supervised and unsupervised learning? In case if you wanted to attend my session, the first 10 minutes it will be Q&A. Every time it will be Q&A. Without that, we won't be getting into that particular day's topic. In that way, we can learn, we can make the learning process more effective. So try your best to prepare yourself before coming and attending my session. Okay. If you're not giving the response, it means that you have not prepared to attend this session. So that will never work. So please come prepared for each and every session with respect to the topic, whatever we have discussed on the previous session. Difference between supervised and unsupervised way of learning. What is the difference between supervised and unsupervised way of learning? So, Astosh, yes, Astosh, great. Srisha, supervised learning also produces output where unsupervised learning can't. So, Srisha, actually, you can fine tune it. Supervised learning is nothing but we have a specific output there. That output feature Y is already defined. That's what the point. So, in unsupervised, we don't have the output. So, Harsh, in unsupervised learning, machine is given raw data without any predictions. Right. We have to understand the patterns. Aditi, in supervised output is known and in a wonderful, Aditi, great. Harsh, in supervised learning machine knows what will be the output. Right, perfect. I think Harsh understood, Aditi understood, Srisha, Astush. All right, only 4 responses. Try to participate on the chat box, others, so it would be more better. So that's what we have covered in yesterday's session, how exactly this live flow machine learning will work. Just we had an introductory part, and also even we worked on that newspaper feasibility prediction based on the daily circulations, what would be the Sunday circulations, we predicted it. So now today we are going to get into this next part, that is deep learning. So as per the plan, so let me show you this. So this is the plan what we had. So we started with the terminology differences and then life cycle, and then Python programming part 2 days we spent, and then Python data structures and Python libraries. And again, 2 days we spent for almost this data analysis. 2 days we spent, and then data visualization we done, and then we discussed about statistics. And then we completed this random variable and probabilities, and then I just devised this particular plan, machine learning. And now we are going to get into this deep learning part. All right, we are already lagging behind 1 day, but that's okay. Let's see how exactly we are trying to cover it. So deep learning. Now we are going to cover these 3 parts. Why deep learning, and some idea about back propagation and different activation functions. So the initial 2 sessions, so today and tomorrow, today is Wednesday and Thursday. Wednesday and the Thursday, it's going to be more theoretical session. And then Friday, we will combine all those theory and we'll be working on one particular script and also how to optimize the neural network performance. So that's what we will be discussing it here. All right. Now let me stop sharing my screen. Let us get into this particular topic. Now, as I used to say, every time, whenever we are learning any new topic, the first question is nothing but why. So we learned about statistics. Why statistics? Because to make a statement about present. We learned about machine learning to make a statement about future. And again, deep learning is also making a statement about future. It is going to understand the patterns. But the point is nothing but, so in deep learning, the data structure, it will be an unstructured data. What is that unstructured data meaning? So now let's say here, now I'm able to have, now my human eye is seeing Harsh Singh and also let's say Aditi Patel. Now I'm seeing both of them only one time. Maybe next time if I'm seeing both of them, I can easily distinguish, or I can easily say who's Aditi and who's Harsh. I can easily segregate between them. So it is nothing but what image classification, right? So my human eye is seeing, and it is a classification thing. So now I wanted to look into an image, and my machine need to go for image classification. So we call it as image classification problem statement. So to perform this kind of, to deal with this images and everything, we can't directly work with machine learning algorithms. So now here, let's say here I'm having, let's say here I'm having maybe Supriya is here. Let's say Supriya is a good singer. Now Supriya is singing very nicely, and now I'm just whenever we are listening to Supriya singing, we all are getting melted. Now I wanted to make the same intelligence, because Supriya is having an intelligence to sing more effectively than others. Now a machine I wanted to build it, which can also sing like Supriya. Now I'm just knocking the door of machine learning. Hey, machine learning, can you sing like Supriya? No, it is saying no, I can't sing like Supriya. So that is also failing. Now here we are having, let's say maybe Galton is here. Now Galton is a good pianist. Let's take it in this way. Now he is just going to an hotel, and he is having one good piano placed at one corner. He's going there and he's playing the piano, and people are totally amazed, and they were giving a good applause. Now one data scientist, he is looking at it, and he's saying, hey, this is an intelligence where exactly Galton is able to play nice. Now can I build the same kind of intelligence to a machine? Can I transfer it? Now again, my question is, can I get the support of machine learning? Machine learning says, hey, no, again, I can't deal with this kind of music related data, because it's all about learning. I have to take the input, and also why input and output, I have to provide it to the machine to learn it. Now, when you're giving the input like images, when you're giving the images like videos, when you're giving images like images and audio, so this machine learning is going to not work with, not going to handle that kind of data sets. Machine learning can handle only structured data. What is a structured data? Row and column format. That's what it is going to handle. Other than that, it is not going to handle it. So to deal with this unstructured data, and also the applications, whatever I've mentioned, and there are a lot of other applications as well, to be honest, but I'm just giving a raw idea about it. So in short, we can say to deal with this unstructured data, so we are knocking the door of deep learning. So now, able to understand the difference between machine learning and deep learning, why we are learning deep learning, is that point clear? I'm just confirming everyone. All right. So now, why that's what researchers also were thinking. Now, here human is having this kind of intelligence. Now, the same intelligence I want to give to a machine, how do I need to do? So that's where, to come up with this images, and to deal with this kind of data, they had an inspiration of human brain. So they are looking into the human brain. I'm not sharing anything. I'm just speaking. So later I'll be sharing some material slowly. So now they looked onto the human researchers. They were looking onto the human brain now, because today in the market, whatever we are saying, all the inventions is happening with respect to humans, because we are having a lot of animals, a lot of species we are having in the world. Only human is able to invent new things compared to all the other species. Now, why human is able to invent some new things which is more advanced? Now, if you look back from the previous century till the today's century, whatever we are living in, so the technology is getting improvised. So day by day, it's a new technology. People are working on it. Why? Because human is utilizing his human brain. So within this human brain, we are having something called as neurons. So a human brain is having more than 100 billion neurons. I think 80 billion neurons we are having in our mind. So because of that, when neurons are getting activated, so my brain my brain is thinking what to do, how to react to this kind of situations. Now that's what it's all about. Neurons, we call it as, since we are humans, I call it as biological neuron. So what is this biological neuron? Now here I'm having I'm just let's say here I'm having Sonia and also Rishikesh. Now, if I'm just making this statement, hey, this third 20 days program is not at all going to help you. Now, Sonia is just getting angry. Hey, I'm just giving my effort and my time to come and listen to this lecture. How can this person say that this is not going to help me? Now, this is how Sonia is getting angry. Now, Rishikesh is there. Now, Rishikesh, what he's doing now, he's thinking, okay, why this is not going to be helpful? Now he's just thinking of some other alternative stuff. So from here, what are the other things that I have to study? So in this way, if you compare Sonia and Rishikesh, the way how their human brain is reacting to the things, it's totally different, right? So it's there are two different things. How exactly for one particular situation, how exactly my brain is reacting, because each and every person will react in a different way. Now if you say our grandparents of our our parents, they used to be easily triggered. Most of them are usually easily triggered, but now today, the young people today in the market today, whatever we are seeing, so we are not getting easily triggered. Even well, let's say we can compare between, I think IPL season is going on, Virat Kohli versus Dhoni. So who is getting easily triggered based on the situations? Virat Kohli, because he's the number of neurons is similar, but the way how neurons is getting activated will be different from one person to the other person. That's why even if we compare us, the brain will accept the things immediately for one person. The brain will accept for some persons, for some learners it will not directly understandable. We have to go through it again and again and again. So it's based on number of neurons is pretty similar, but activation, how exactly brain is getting activated, that will be different from one person to the other person. So now we have different activation functions we'll be studying one by one. But the point is nothing but researchers, they were looking into this particular human brain, and they were thinking, okay, this is how the brain is getting activated. Now what they are doing, now they are just tested with something called as, now whenever even if you see some movies or so here whenever they are coming up with some new tricks or new thing, they used to test it in mouse. So why? Because this mouse used to have lot of neurons. Second rank goes to this. Why? Because now here let's take for example, now Srisha is here. Now Srisha, let's say she is staying in her good house. Now she wanted to go for 1 month vacation with her family. She's going there, and after once she comes back, now when she looking into the kitchen is completely a mess. What had happened? She has hidden some snacks somewhere. Now this rat has found this particular snacks, and it made a hole, and it made this particular complete kitchen a messy. Why? Because now even after you clean it, and even if you find some, if you're fixing it, this rat is going to find, it will try it best to find another way to come and take this kind of things. Now why? Because rats will always try to escape. That's because it will always find a way to escape, so it is using its brain. So that's why the second rank goes to this particular rats. So now when I'm having more number of neurons, if this is properly getting activated, now that's where we are getting more intelligence. Now again, they were researchers were thinking, if a human uses his brain completely, let's say 100 percentage, now what will happen is nothing but our brain will get exploded. Why? Because even whenever we are listening to this lecture, maybe some of you will be taking it very easily, but some of you, your neurons will get triggered, and you will slowly get headache, and you're slowly all these neurons will get hit again and again and again, and finally you will feel headache and you wanted to go for a sleep. So now again, that's why researchers say nobody can use their human neurons or the brain to the fullest. In case if I'm using to the fullest, what will happen? Maybe if you have watched this Lucy film, so but you might get to know, if I'm using this particular brain to the fullest, my brain will get exploded. So that's something very real here. That's what the point is. Nobody can use it. Even Albert Einstein, he has used only 2% of his brain. That's what even he says. So but he came up with a lot of new inventions. Now we are here. Now that's what research is also saying. Okay, because of this neural network architecture, biological neuron, we are able to come up with a new inventions. Now what they are doing, they are just looking into this particular neural networks. Now let me share my screen. See this. This is the biological neural network architecture. I'm just going to get into Google. See this. Let me show you this biological neural network architecture. Biological neuron. See this. So this is one neuron here. So in this way here, if you see this is my nucleus, and here we are having this is a one neuron. Here we are having dendroids, and the information is getting carried by this something called as axon, and this axon is having the terminal. And to this particular terminal, and another neuron will get connected, and to the terminal of this axon, another neuron will get connected. So in this way, 80 billion neurons is getting human brain is having, because of there is a connection between one neuron to the another neuron to the another neuron, and there is an lot of interconnectivity between this particular neurons. Okay, now researchers they were looking into it, and based on that, now this is a biological neuron, human way of learning the things. Now they have to make it something like artificial. So here this is a biological neuron, and they just came up with something called as, they wanted to build something artificially, and they built it finally, and they named it as artificial neural network. We call it as ANN. So up to this, able to understand? Based on the inspiration of biological neuron, they looked onto this researchers, and they came up with something called as ANN. We call it as artificial neural network. How exactly that network will be, we will be seeing in some, we will be seeing now. But up to this, able to understand? Harsh, Srisha, others. All right. Supriya is fine. All right, Chaitanya, fine. So let me again stop sharing it. Let me again ask you something. All right. Let us go back to the human brain itself. Now, I just wanted to ask this: is my human brain, is it actually learning or adopting to the circumstances? I'm just getting a question. Now, what do we mean by actually learning or adopting to the circumstances? So here, I used to give this example every time. So now here, let's say here I'm having maybe Srisha's here. Let's say Srisha is good at having cappuccino. There is one cafe coffee day nearby her place. So she's good at having cappuccino. She likes it very much. Now the input is nothing but what she's taking is nothing but cappuccino. Let's take it as nothing but X. And what she's claiming is nothing but Y. The output is nothing but it is good. Input is X, that is cappuccino. Output Y is nothing but the taste of the cappuccino is good. That's what actually she is claiming. Now Srisha is inviting her friend, maybe let's say Chaitanya. Hey Chaitanya, why don't you come with me? This cappuccino will taste good. Now Chaitanya is having in her mindset, hey, I don't like this cappuccino. But anyway, because of Srisha, she's inviting me, let me go. Now Monday they both are going. Now Chaitanya is also having a sip of this particular cappuccino, and she's just her what she is saying, she's tasting it, but her mind is not accepting the taste of it because it's something very bitter, and she's not liking it. But actual output, what Srisha is claiming is nothing but it will be great. But what Chaitanya is saying for the day one, hey, it is not something good. Now second day also Srisha is inviting Chaitanya, come on, let's go. Now Tuesday they both are going. Now Chaitanya is having the same thing, but the way how she is feeling now is far better compared to Monday. Now she is getting used to it. Okay, it's fine, not bad. Now Wednesday again, Srisha is calling Chaitanya, let's go. Now without a second, no second thought, Chaitanya is just going over there, and they both are having. Now she is feeling good. Now Thursday, what is happening now? Chaitanya is inviting Srisha to go and have a cappuccino. Now what had happened? The input is not getting changed. That is cappuccino. The actual output, that is Srisha's actual output, that is a cappuccino tasting good, that is also not getting changed. But what is getting changed here is nothing but the way how Chaitanya brain is taking the things. So we call it as getting adopted. So the same input, but the same output. But what exactly it is getting changed, we call it as weights and biases. Now just take a look at this particular screen. Whatever we learn, let me just show it here. See this? Deep learning, human way of learning. So actually, the very simplest way we can say how exactly human is learning. We can say y is equal to wx plus b. Just remove this af. We call it as activation function. Without this activation function, wx plus b is very similar to which equation? What do you see? This equation. This equation is very similar to what equation? Mx plus c, equation of a straight line. Wonderful, great. Right. Straight line, correct. So now I want to understand, let's say, why this activation function will come back after some time. But with respect to this equation, so instead of mx plus c, I'm just giving wx plus b. So now what is this? Y is nothing but the output. What is the actual output? Actual output is nothing but it tastes good. X is nothing but input. What is the actual input? Cappuccino. And what is this W? We call it as weights, and B we call it as biases. Now W is nothing but it is nothing but an importance. So weights is nothing but importance. Bias is nothing but errors. Now if you want to, if you just take a complete look at this by using this particular equation, that's how my human brain is learning. How exactly it is learning? Now I'm just drinking cappuccino. Output is nothing but it is tasting good. Now see this. My input my input is not getting changed. My output, actual output is not getting changed, but my weights and biases will keep updating in my human brain. How it is happening? It's nothing but what is the importance of W? So it is, I'm just mentioning it is importances. Now, how I'm saying it is importance. Now, whenever I'm just delivering a content, right? So AI related content or machine learning related content, I'm saying, hey, this particular topic is very much important. Just to give your complete attention. Where exactly, whenever I'm trying to deliver the content, there is some importance associated with that particular content. That is nothing but weights. Bias is nothing but when you are, when from the learner side, maybe from YouTube or from Zoom, when you're watching this lecture, from your side, whenever you're listening to the lecture, your human brain automatically will add some bias. What is that bias? Now, can you just tell me whatever I'm explaining, 100% is it getting into your mind? 100% whatever I'm delivering, is it getting into your mind? Anyone? Not possible at all. So maybe 90% we can say, or 70% we can say, 95. Yes, Harsh. So the point is nothing. Maybe you might have studied about this deep learning already, and you maybe try to evaluate with whatever I studied and whatever I'm listening here. Is it right or now? Hey, I've already studied there. Now whatever John sir is teaching, it is completely some completely different. Now what is this? Now here your mind, that the one who's delivering the content, he's not going to add any bias, but your human brain, when you're receiving the things, it is going to add some bias into your human mind. So the bias, that's what I used to say. Initially, the day when what Chaitanya said, hey, this cappuccino does not taste good. Now bias, her human brain, by naturally, it is just taking it. So that's what the human brain is all about. Now, both weights and biases I have to optimize in such a way that my actual output will be matched. Now see this, what I'm doing, how exactly it will be done. If you look onto the story, what I've done, Monday, Tuesday, when every day she's going and she's taking the same thing. How exactly is happening now? Repetition. That's what here I just mentioned here. There are three building blocks of human learning process. One is batches, second one is learning rate, third one is iterations. So there are three building blocks of human learning process: batches, learning rate, and iterations. Now, what is batches? How human brain will learn more effectively. Now, every day, this is a 20 days of EDL program, everyday learning program. Each and every day we are having an agenda, we are learning it. I can't teach you, even your human brain will never take all the topics within one day. Even if you find a lot of YouTube videos like 10 hours lecture, 12 hours lecture, you can't sit at one stretch and learn everything. You need some intervals. Okay, today let me take 2 hours of lecture, maybe tomorrow 2 hours of lecture. If you are just superimposing your mind to understand or to learn everything, so your mind will never take it, so it will feel exhausted. So Every day, your human brain will learn the things portion by portion. So the first block is nothing but portion by portion. That is the first building block we can say. Second thing is nothing but learning rate. Now, what is this learning rate? Now, whenever we are listening to this deep learning and everything, we are going with a slow pace. Now, I can't go with the very fastest pace to complete the syllabus or to complete this particular 20 days of program. Slowly, we have to march forward and learn it. So second important thing is nothing but learning rate. How exactly we are learning the things with what pace? That is very important. Third is nothing but iterations. What is iterations? How many times I'm watching this recording or how many times I'm reading this? Let's say deep learning introductory session today, it is not understandable, but you have given your best to understand. So today 50% you understood it. Now, when you're watching the same recording again, you might get it 85% or 80% we can say. Third time you will be very strong on your particular content, what we have delivered. That's how your human brain will take. The similar way, what exactly will happen is nothing but now input is not going to get changed, output is not going to get changed, only W and B is going to get changed. Now to prove this particular point here, I've just taken on mathematical equation where exactly here I'm just given y is equal to wx plus b itself. Now where exactly I have to make this y is equal to 10 and the input what I'm going to give is nothing but 3. All right, why it should be 10 and input is nothing but 3. I'm going to initialize this particular W and B with the random numbers. Let's say W is equal to 0.2 and B is equal to 0.1. It's basically random numbers. Now, output Y is equal to 10. I have to make LHS equal to RHS is equal to 0.2. That is nothing but W multiplied by X is nothing but 3 plus bias is nothing but 0.1. Now I got 0.7. So is LHS equal to RHS? No. So I need to go for second iteration by taking the same input. So input is see this 3 and output also remains the same. Now what I'm changing is nothing but weights 0.1 and bias 0.2. Now is LHS equal to RHS? No. Now again I'm going for the third iteration 10. So X is not going to get changed. So what is this particular W 0.3 and bias is 0.1. So 10 is it equal to 10 1.0? No, LH is not equal to RHS. Now let me see. W is equal to 3 and bias equal to 0.5. Now 10 is equal to 9.5, which is approximately equal to RHS, sorry, LHS. Now this is what the point is. Now if you see input and output, that is not going to get changed. Only my weights and biases will keep updating itself with multiple iterations to make sure LHS is equal to RHS. That is, we are expecting the actual output to be 10, but the input whatever I'm giving, that remains the same. By optimizing the weights and biases, my brain is going to learn it. Able to understand my point, everyone? All right. Fine. Now that's what here also I just mentioned it. So if I wanted to optimize this particular network, weights optimize is nothing but I want to get best weights and biases. That's what the thing. If you want to optimize it, I have to make LHS is equal to RHS. So for that, we are having different loss functions, cost functions. So we will be coming back to this particular point in a while. Now see this. As I said before, now researchers, they looked onto this biological neural network architecture and they wanted to build it artificially. So we are naming it as artificial neural network. Right. Now to build this artificial neural network manually, so we are having certain, again, there are 6 building blocks we can say, where the three building blocks of human way of learning will be included. What are the 3 building blocks of human way of learning? Three building blocks of human way of learning: batches, learning rate, and iterations. So along with that, iterations is also called as epoch. Along with this 3, we are having different optimizers. Different, why optimize is nothing but because I have to get best weights and biases. For that, we are having different optimizers. And the next one is loss functions. We are having different loss functions as well. And sixth one is activation functions. Different activation functions we are able to have. So these are all the 6 building blocks to build this artificial neural network. All right, note it down. We will come back to it sometime. Now see this, how they are building, because there is a connection between one neuron to the another neuron. Basically, we have to establish that particular connection. Now here I'm just giving two networks. Just tell me which network is the best one. All right. So here, if you look onto it, case one is nothing but, let's say here I'm having a structured data, x1, x2, x3. You're having one particular structured data. All right. So since you're having only three columns, I've just given this is my input column. Sorry, we can say input layer, and directly my output layer. There are two layers I'm having in my network. Now, if you see this particular input layer, I'm just going to pass x1 because only three features I have: x1, x2, x3. I'm just going to pass it, and this is going to get connected to the another neuron. Next layer is another neuron. So now I'm just going to take this and I'm just giving it to the next neuron, where exactly this is my next neuron. So now, to push your information, that's what I said. Whenever I'm delivering the content, I'm going to give with some weightage. So W1, W2, W3. I just given some that particular thing. Now, whenever you're receiving your human, the receiver side always will add some bias. So I've just given one bias to it. Okay. And now, so this particular neuron, we call it as a neuron. This is one neuron, this one neuron, this one neuron, one neuron. This neuron, otherwise we call it as nodes. It is also called as nodes. We can also call the particular thing as nodes. Now, if you see this output of this particular neuron is nothing but we are just going to make a prediction. Screen is not visible. Oh, screen is visible, right? Srisha is saying it is not visible. Is my screen visible or not visible? Others? Once confirming. Srisha, it is visible for everyone. Maybe you can. Okay, thanks for confirming. Maybe you can re-log in, leave the meeting and re-log in. I think it should be fine. Okay. All right. Now see this. Now this particular neuron need to make a prediction. Where exactly in yesterday's machine learning part, after learning, I'm just going to pass this particular newspaper input and output I'm giving it. Later, what would I do? After learning the things, post model training, in model testing, what we have done? We have provided only the inputs. Let's say this network got trained well. Now, this network, this neuron need to make a prediction. What is this prediction? Let's say I'm just going to send some inputs like 1, 2, 3, some inputs. The actual output for the first observation is nothing but 100. Now, this is making a prediction. If it is making a prediction 100, then it is not a problem. So, but this neuron, let's assume it is making a prediction of 50. All right. So now what I need to do, I have to calculate the error. Error is also called as loss, or we can also call this as called as cost. So error function, loss function, cost function, these three are very similar terms. Now the actual output is nothing but 100. Now let's find out the difference between actual minus predicted. That's what this loss is all about. Actual is nothing but 100 minus predicted is 50. Now this loss, it should be equal to 0, or we can say it should be close to equal to 0. If the loss of it is 50, then it means that my model did not learn well. So I wanted to minimize this particular loss. So to minimize this loss, how do I minimize it? Through back propagation, loss function will be reduced. Now from this particular part, again I have to back propagate. Again I have to take some other data and learn it to make sure the prediction is going to happen well. So through back propagation, loss function will be reduced. Even that's how human brain is also working. Now here we are having Aditi Patel. Now after learning machine learning for one day, he's trying to go and give some interviews. Now in machine learning itself, there is a lot of things to learn. But with one day session, he's getting more confident and he's just giving one interview. Now he's just failing in that particular interview. Let's assume it. Now what need to be done? If he's just feeling very sad about it every time, lot of times, not working on the things, it is not going to work. So what he need to do? Again, he need to go back propagate, and then he has to read a lot on the same topic or some new topics. So that's what it is happening. So through back propagation, loss functions will be reduced. Maybe next time if he's just going and facing an interview, it will be more better. So I need to back propagate from here to the input neurons, and when I'm just back propagating, weights and bias optimization will happen. So for that, we are having different optimizers. We will be looking onto it. All right, so this is nothing but I think you should be able to understand this particular point. But again, if you look onto it, so I'm having only 3 neurons. and directly one output layer. So is case one better, or I'm having a second neuron where exactly I'm having input layer, hidden layer, and output layer. Totally three layers I'm having in my hand. So my image is nothing but it is a image related data or video related data. So where exactly I'm creating n number of features here and hidden layer, n number of neurons, and one output layer. So this output layer, or we can say this output node, need to make a difference between whether it is Astush or whether it is Aditi. All right, so that's what this particular neuron need to do. So now what I'm doing, so this neuron, I'm just giving it. So do you think case number one or case number two will learn better about the problem statement? Which one will learn better? Which network will learn better? Case one or case two? Case two. Why case two? Why case two? Since it's a multi-layer, as inputs are more. Based on the input Supriya, we don't make it. Basically, here we are having one hidden layer. Basically, the number of neurons is getting increased, right? Instead of directly giving into output, I'm trying to take the input neurons, trying to connect with another hidden layer, and maybe I can increase the number of hidden layer I want. So in this way, there is a lot of interconnectivity is going to happen. So based on that, the learning is will be far better compared to a simple uh, neural simple feed forward network, we can say, like input and only the output layer. Right, Harsh? Correct. So, and again, there is one particular problem if you just keep increasing it, but that will be discussed, that can be discussed later. But here the point is nothing but I'm having many inputs, or we can say n number of inputs, but the hidden layer also I'm just trying to connect. So if you see, when I'm trying to send one information from one neuron to the another neuron, I'm just pushing a weights. But when I'm receiving it, bias is going to get added. And even from hidden layer to output layer also, I'm just the weights is available. But again, on the receiver side, bias is going to get added. So now what need to be done? If this network need to train well, forward propagate and back propagate. And when we are going for back propagation, weights and biases will get optimized. Now, when I'm forward propagating it again, take that new weights and biases, optimize the network so that the loss function of the network will be reduced. Got my point, everyone? Wonderful, great. So here, see this iterations and epoch. Here I just mentioned it. So in forward propagation, weight initialization happens. In back propagation, optimization happens. Now there is something called as you can explore this just for the purpose of understanding. TensorFlow Playground. Just go to Google and just give TensorFlow Playground. So here you can just see there's nothing but epochs. Epochs is nothing but the other term of iterations. All right, see this learning rate I have, activation function I have, and everything. Now this is your data set. Okay, so for this particular data set, you have to make a good decision boundary so that later classification will happen better. Now what I'm doing, I'm having two hidden layers. So one hidden layer and second hidden layer, and directly it is going to get connected to the output. Now what is the loss for now? That is even before training, the loss itself 50%. Test loss is 50% and train loss is 511. Now what I need to do is nothing but see this activation function, everything I've just selected. Now I'm just going to start my network. Now before that, let me check out the weights. So the weights of this particular blue color line, where exactly X2 is to connecting with the fourth node of first layer of this particular neurons, 0.46. Let's observe 0.46. Let me start training. Now loss is getting reduced, and this is 0.45. I'm getting a good decision boundary. The test training loss is 0.01. Test loss is this. Let me maybe stop it. If you now see 0. Now it is 50. Now, but if you look onto it, so now I got a very good decision boundary. So what is really required here is something epochs, number of iterations. So 482, what does an iteration mean? Why I have to go forward and backward. So one forward and backward propagation, we call it as one epoch. So that's what, so here 482 times I just went forward and came backward. That's what this particular epoch is all about. And because of that, I am just able to see a very good decision boundary like this. All right. So the point here is nothing but input is not going to get changed and the output is nothing but I want to get a decision boundary. For that, my weights and bias. So here with internally within this neuron, bias will get added. Here it is not shown, but bias will get added for each and every neuron over here. Now able to match up with whatever I've explained so far. Perfect. So maybe you can just explore this TensorFlow playground after some time. That should be also great. Okay, the name is TensorFlow playground. All right. Now let us come back here. That's what here I just mentioned. Iteration is nothing but forward propagation. In forward propagation, weight initialization happens. In back propagation, optimization happens. Very important point to be noted. All right. Now, let me just give you one equation. You can note it down. This is my input layer. Input layer. Hidden layer. Output layer. All right. So we call it as a multi-layer neural network or multi-layer perceptron. That's what the term here we call. Input layer, let's say 1, 2, 3. So here it is. X1. So totally I'm having 3 inputs. Where exactly it is getting connected to. Each and every neuron will get connected to the next layer's neuron. H1, H2. So here I'm having one neuron. So here let me give a name. W11, W12, W21, because 2 to 1 it is going. W22, W31, W32. So here let us keep a name W5 and W6. This is the thing about output Y. And receiver side, bias 1. So here I'm just going to give bias 2, which is going to hit to the output node. Now, I just want you to make this kind of equation. The output of, can you just give me the output? Maybe we can say input of H1, or we can say H1 is equal to what? W11 X1 plus W21 X2 plus W31 X3 plus bias 1 multiplied by activation function. All right. H2 is equal to what? Activation function multiplied by W12 X1 plus W22 X2 plus W32 X3 plus bias 1. Now what is the output of Y? We can say 1 minute, not the output. We can say Y is equal to what? Activation function multiplied by W5 H1 plus W6 H2 W6 H2 plus bias 2. All right, able to understand this mathematical equation? Sorry, here I was a bit bad, but able to follow this? So this one you have to manually write it and see. Only then you will be strong in this particular areas also. So this is what we call it as perceptron or multi-layer neural network, we can say. The input layer has some neurons. It is going to get pushed into the next layer, hidden layer, and from the hidden layer, it is going to head to the output layer. So now this is a very basic neural network architecture. So from here, when we start to work on some scripting part, you will be clear in that is Friday. You will be very clear with whatever we learned. All right, just take it as note down all the theoretical points. So even that's what the calculation I have done it over here. Since I've given 3 H1 H2 H3, I've given H3, and Y is nothing but so activation function multiplied by 3 weights and 3 hidden layers. That's it. Up to this clear, everyone? All right, Jyoti has responded. Fine. So this is nothing but the basic introduction of this particular neural network. Now we will be taking a break, and post break we will come back and we will be learning about. And one more thing, just let's complete it and then let's take a break. See this. Here I just mentioned Wx plus b, and before that I've just added one term, activation function. Now what is the purpose of activation function? See this. If it is just Wx plus b, it is going to learn this complexity of the data set, right? Just a linear line. Now, instead of this particular linear line, if I'm just keeping this activation function like a activation function multiplied by Wx plus b, that activation function, it can be actually, there are a lot of different functions we have, but for a specific reason, we are trying to keep that activation function as non-linear activation functions. So we are having list of non-linear activation function. The first one is sigmoid activation function. So now see this. Let's say sigma multiplied by, if you just give Wx plus b, let's say you're getting a result of minus 5.25. Now 1 by 1 plus e to the power of minus 5. Sigma is nothing but 1 by 1 plus e to the power of minus 5. That's the equation. Now by doing this particular equation, you will be getting a value between 0 to 1. So now let's say if this particular value, if it is between, if it is like minus 5 to 2.5, your and if the activation function, because each and every node has an activation function multiplied by Wx plus b. If it is a negative activation function, because sigmoid curve, we all know that it starts from 0, right? 0 to 1, that's how it will take. Now the value of this is minus 5.25. So now what will happen? After solving this, after y is equal to 1 by e to the power of minus 25, after solving this, let's say if you are getting this, but mostly you won't get it because the values will be between 0 to 1 itself. So if it is between 0 to 1, you can get the values. In case if it is less than 0, this value will get, this value will never be passed, or it will be made as 0. Or if it is greater than 1, let's say 10, 15 or something, it will be equated to 0. So or else what if it is less than 0, it is going to make most of the neurons dead. All right, most of the neurons did. So why activation function? There are two reasons why we are looking into activation function. First reason is nothing but to learn complex pattern from the data, because without this activation function AF, it is a linear line. Now I wanted to, my data is completely completely complex. We can say we are going to deal with image data, video data, and these are the data. So those data, it is not a linear data. It is something like a non-linear data set. So to deal with this non-linear data set, I need a non-linear activation function, but by using mathematical equation y is equal to mx plus b. So now to learn the complex pattern from the data, we are using it, and to decide to decide which neuron need to be triggered. So whether this neuron need to be triggered to the next layer or this neuron need to be triggered to the next layer, which neuron need to be triggered is also decided by activation function. Got my point, everyone? Got it? Somewhat, not exactly. All right. Anyway, today's session and tomorrow's session, I'm not expecting 100% of your understanding here, because everything you can combine it in scripting and you will be learning it in a more better way. So, but whatever you're learning here, just take it as a practice or learning. So when we are coming on Friday, we will be working on one particular script which will help you to understand or relate whatever we learn so far. All right, fine. So now let's go for maybe 7 minutes break. You can take it since it's a theoretical session. Let me increase your time, increase your break time. 7 minutes timer. Is that okay for everyone? 7 minutes. All right. So let's go for 7 minutes break now. So post break, we will come back and we will be looking into what are all the different activation functions available, the different optimizers available. Let's take a look at it, and we will be learning something called different activation functions. What are they? We will be understanding it today. Okay. Let's go for break now. 7 minutes break. Let me start the time. Yes, let's go for Hey, hi everyone. It's all back from break. Rishikesh. Okay. All right. Fine then. So till now, what we are discussing is nothing. What we have discussed is nothing, but we understood the difference between machine learning and deep learning. Why we are getting into deep learning, we discussed, and what is the limitation of machine learning, we understood. And then we understood, we looked into how exactly human brain is adapting to the new circumstances by optimizing the weights and biases. That's what we looked into it. With respect to simple mathematical equation, we have understood that. And then we understood about how exactly this biological neural network architecture would be. And based on that inspiration, how researchers they came up with and they got into this artificial neural network, neurons and everything, we learned it. And what are all the building blocks of a human brain? So that researchers they have taken and they have given it to building this artificial neural network. There are 6 building blocks we understood. So that's what we have that's what we have covered, and also we have understood about multi-layer neural network and single layer neural network. With respect to single layer neural network, the learning is not going to be more effective. So we are preferring multi-layer neural network, which is also called as multi-layer perceptron. All right, very important term. So where we are having input layer, hidden layer, there are 3 layers we are having here: input layer, hidden layer, and output layer. This is how they constructed this artificial neural network. So we can have only one input layer and n number of 1 minute. So we can have one input layer and n number of hidden layers, one output layer. That's very important point. How many input layers you can have? One layer. How many output layer you can have? One layer. How many within that layer you can have any number of neurons. All right. And how to decide that neuron, again, once we get into scripting part, you will be understanding it. And we can have n number, any number of hidden layers when we are constructing this artificial neural network. Then we constructed it. We understood how exactly by using one mathematical equation, that is y is equal to activation function multiplied by wx plus b. By using this particular mathematical equation, how exactly neural network is getting trained or learned, we discussed it. So, and also mathematical explanation also we have understood. Then we understood the purpose of activation function. Why we need activation function? Because to trigger a neuron, and this all the activation functions are completely, we can say it is non-linear activation function. So these are all the pretty important points to be noted. All right, maybe you might not get all the stems whatever I'm explaining on the day one, but just go back to the recordings before coming and attending the next lecture, because this is something your machine learning and everything is like one first standard or second standard syllabus. This is directly like 10th standard or 12th standard. So the topics, it will be a bit complex compared to whatever we learned. But once we have completed this theory, then if we get into the scripting part, everything you can combine it and you can find it very much easier. But until then, the foundations will be pretty difficult to, or we can say pretty challenging, not difficult, pretty challenging to understand it. All right, try to give your complete attention. Right now, we learned at one point I just mentioned there, that is in forward propagation, weight allocation happens. In back propagation, I mentioned that optimization happens. Now, see this. Back propagation is something very important. Why we are back propagating? Because when we are forward propagating, we are calculating the output. So my network is predicting the output. When the Y prediction, that is the model prediction, is it equal to actual prediction? No. Then how to find out the losses? Actual minus predicted. So that's what we call the loss function. That loss function need to be close to 0. If it is having some value, it need to be reduced. How it will be reduced? I have to back propagate. So the back propagation major reason is nothing but I need to optimize my network. What do I mean by optimizing the networks? I have to have better weights and biases. Initially, it is a random weights and biases. See this, that's what even we are seeing it in the network. So before we get trained, if you look onto it, weight is equal to 0.07, 0.02, some random weight is getting done. So how exactly this random weight is getting initialized? When we are constructing our neural network, we say, hey, take the random numbers from normal distribution, take the random numbers from uniform distribution. So we try to mention that. So basically it is going to take the now random numbers from a normal distribution itself. But if we want, we can also change that. But again, we get into scripting part, we can discuss more about it. But now the point is nothing but random weights and biases will get optimized. Now, once the training was started, let's say I'm just looking onto it, this layer 0.48, where exactly, see this, I can have any number of hidden layers and any number of neurons within a network, all right, but I can have only one output layer, right? Now, let's say, let me delete this. Maybe two layers is sufficient, and just to understand it. So this line 0.24 random weights. Let me start training it. 0.49 after some iterations, 0.65. So the point is nothing but the forward propagation, backward propagation, forward, backward. In this way, I'm going for multiple iterations. Slowly, the loss function is going to get reduced. So how exactly this back propagation is happening is nothing but there is something which is a bit complex to understand, but you can just note it down. Don't try to get into that more. It will more confuse you maybe. It's a lot of 12th standard math, how a first standard or second standard student, if he sits in 12th standard, that's how the mind will be. But we have already studied it. There is something called as chain rule of differentiation. So by using this partial, 1 minute. Yes. So by using something called as partial derivative functions, that is, which is coming inside your in your calculus subject. So that's what it is getting used here. Maybe if you have studied in depth about this calculus subject in your 11th or 12th standard, or maybe if you're a commerce student, you might be able to understand this particular part. Now, see this, how exactly backward propagation is going to happen. Let me share this particular screen. Just give me a minute. Let me share this. Just take a look at it. So what is this backward propagation? I would be just quickly showing this. So this is not something very important to sit and manually write and understand. But if you're doing it, you will be very confident on how exactly it is going to happen. So what is back propagation? Back propagation is a supervised learning algorithm for training neural networks. A simple neural network will look like this, where exactly I'm having input layer, hidden layer, and I would be having an output layer, right? Now, why we need back propagation? Because here I'm having input layer, and to push information from one layer to the another layer, we are having weights and hidden layer, and weights we are having it. Okay, so now we know for better optimization. So here we have given some random numbers like input 1, input 2. Weights are a random number, 0.11, 0.11, everything, right? Now, after this, what we are doing? So here, the output layer here, what we are predicting is nothing but 0.191. So here what I'm doing, this prediction, input is nothing but 2 and 3. Actual output, what is the actual output that we are expecting out from this particular neuron is nothing but 1. This should return 1, but this is giving me 0.191. All right. So how it is giving me this particular result, we need to calculate it. All right. So how we can do this particular calculation? Let me try to help you out. But anyway, in the next slide, we will be doing that. All right. So this is trying to give me 0.191. Let me do one small calculation. So this is 2, right? Let me take this pen. Okay, 2. So this is weights W1 and it's nothing but X1. All right. Now, what is the equation of this? H1 is equal to activation function multiplied by Wx plus B. Okay, that's what. So this W, what is this W and B? We have to find it. What is this X? We have to find it. And then activation function, we have to substitute it. All right. This activation function can be anything. E 1 plus e to the power of minus y, and or we can have e to the power of xy minus e to the. This is again a mathematical equation. We will be learning it in a while. Now, by using this, you'll be having this particular value. Now, output actual output we're expecting 1, but the model is giving me an output 0.191. Now, what need to be done? Error. Error can be of any method. So that's why we are having different loss functions also. 1 by 2, I'm just taking prediction minus actual the whole square. So if error, if it is equal to 0, the prediction is equal to 0. Sorry, the actual minus is equal to prediction. That's what we are expecting basically. So, but what is the error that we have got it 0.327. So this need to be optimized. So in order to optimize this, we are going for back propagation. So to optimize this particular network, we are having different optimizers. One of the optimizers is gradient descent. So update the weights using gradient descent approach. All right. So gradient descent is used for finding the minimum function. In our case, we want to minimize this particular function. Let's say, maybe we can think of it. Let's say here I'm having maybe Supriya's here. Let's say Supriya's dropping one ball from the top of the bowl. So that ball need to quickly come down and it need to reach at this particular bottom position. Where exactly, if you look onto the x-axis, we call it as a weights, random weights. That the weights can be of higher weights or the lower weights. That's not any because it's a random number. But what is the y-axis? Nothing but squared error, or we can say it's a loss function. What is my goal? I wanted to reach this particular position as quick as possible. So this position is where this loss function is equal to 0. All right, where the ball rests, that position is nothing but the where loss function is equal to 0. Where loss function is equal to 0, we call this a global minima. All right, so note down this particular term. Where loss is equal to 0, we call it as a local minimum. Sorry, global minimum. So to achieve this particular global minima, I have to move from this particular position. I have to move here, move here, move here. So if there is a higher weights, I have to lower the weights. If it's a lower weight, I have to increase the weights and I have to slowly come down over here. That's what the point. To get this better weights and biases, I'm relying on a lot of optimizers. One of the optimizers is gradient descent. All right. Now, this is just something, an overview, where exactly you are going to prepare a model. And this model is going to give you a prediction. You're going to calculate the error, y predicted minus y actual, the whole square. And is the error minimum? If the error is minimum, model is ready to make prediction. If it is not minimum, update the parameters. All right, update the parameters and train it and again update it. In this way, it keeps going on. Now, see this a simple network we have just taken. Where exactly input 1? I'm just trying to push a new network. Sorry, to push information from one neuron to the another neuron. As I said, W1, W2, W3, and also all this receiving side is going to get one bias. So bias 1, bias 1. Here also W5, W6, W7, and bias 2. Now I just initialized all the weights inputs with some random numbers. Let's say input 1, input 2 is equal to 0.05, 0.10 I've given it. And W1, W2, W3, W4, W5, W6, W7, W8, everything is having some random numbers for better understanding. That's it. And B1 is nothing but 0.35 and B2 is equal to 0.60. That's what is random number I've given it. So what is the actual output we are expecting from this particular neuron is nothing but this should return 0.01 and this should return 0.99. That's what we are expecting. All right. Now, in the forward pass, what is happening? We know that the equation. All right. Equation is nothing but W1x1 plus W2x2 plus bias 1. All right. So now here we are at this particular position. Now, what is the equation here before using activation function? That is Wx plus B, right? So W1 is nothing but because here we are getting two inputs. W1, that is 0.15 multiplied by 0.04 plus What is W2? 0.20 multiplied by 0.10 plus bias one is that is 0.35, right? So we just multiply 0.35 multiplied by 1. That's it. So we get the 0.335. So this 0.335 need to get the positive activation function, because here I have not used any activation function. Wx plus b plus 1, Wx plus, that's what I've used it. Activation function. The activation function I'm just using is nothing but sigmoid activation function. Sigmoid activation function is taking one mathematical equation where exactly sigmoid is equal to 1 by 1 plus e to the power of minus y. All this y is nothing but 0.337. So 1 by 1 plus e to the power exponential term, if you do it, this particular term, you'll be getting 0.5932. In a similar way, if you calculate this, like what is the calculation? 0.20 multiplied by, this is coming in, sorry, W3, 0.25 multiplied by 0.10 and 0.30 multiplied by 0.10 plus 0.35. So you'll be getting 0.59. And after passing through sigma, you'll be getting this. Now we got H1, output of H1 and the output of H2. Now we have to send it to output of O1 and output of O2. See, next screen. All right. Output of O1 is nothing but what I get, Wx plus b, 0.4 multiplied by 0.4 multiplied by output of H1 is from the previous stage, 0.59 plus 0.45, that is 0.45 multiplied by output of H2 is 0.59 and plus bias is nothing but 0.60. You'll be getting 1.10. Again, what is the activation function here? Sigmoid, 0.75. Similarly, we'll be getting it here. Now, if you see, what is the output of O1? 0.75. What is the output of O2? 0.77. But what is the something we are expecting? So here we are expecting 0.01 and here we are expecting 0.99. So here it is a problem. Sure, Chaitanya, I'll be sharing it. So here it is a problem. So this document will take a lot of time to understand. So here it might seem easier, but when you're going to the next slides, it'll be a bit difficult to understand because a lot of new partial derivatives, everything is going to get into the picture. Maybe most of my learners will get a little bit confusion here, but slowly if you're doing these calculations manually in your hand, it will be more understandable. Okay. Now we got this output. Now what we have to do, forward pass is done. With the initial weights and bias, forward pass is done. Now we are expecting 0.01 from this output of O1 and we are expecting 0.99 as an output of O2. That is not happening here. So what need to be done? Calculate the loss. Calculating the total error. C total is nothing but 1 by 2 target minus. So this is the loss function that we have selected. All right. So now we are having two neurons here. So what we can do is nothing but, so here we have to calculate and here we have to calculate and totally E total we have to calculate it. So output of E output 1 is nothing but what? 1 by 2 we are giving it. Target output 1 is nothing but what? 0.01 minus output what we have got is nothing but 0.7513. That's what the output. If you're calculating is 0.27, that's what we are getting it. All right. Now the similar way E2, output of E2, the loss function if you're doing is 0.02. So totally if you're calculating it, that like total error 0.29. So this 0.29 is the first forward pass with the initial weights. I got this particular point. Now this loss function need to be reduced. So now if this loss function need to be reduced, what need to be done? If this loss function need to be reduced, what need to be done? If this loss function need to be reduced, what need to be done? Change weights. How can I change weights? How can I update the weights? Change weights and biases, right? How can I change weights and biases? How it is going to happen? Wonderful, Aditi. By backward propagation. All right. I have to go back and I have to do it. So let me go back. Back propagation, yes. So from the output layer, if I wanted to go back and update the weights, see this, we have to update the weights of this particular W5. So with respect to E total, how much I have to change this W5, it is going to impact the E total. So basically I have to do this. So E total divided by W5. to update this particular W5, I have to do this particular part. From this E total, E0, E output 1. So E output 1 is having this output 1. So from this is the connection what we are having it. From the E total, this W5 is having it is that this particular position, right? So from here, we calculated, let me just give it. What is the connection? We have to check it. So this is a bit difficult to take it. Just see this. So here, what from here, what we have calculated, E output 1. So here we have calculated output 2. So together we have found out E total. So now E total equation is E output 1 and 2. So E total, how much E total will change if I'm changing W5? So there is no connection between E total and W5 here. So to establish this connection from E total, we have to go to E output 1. From E output 1, we have to go to this output of O1. And from here, we have to go this particular position. All right. So this we call it as chain rule of backpropagation. Only then we should be able to reach it. All right. In the similar way, how to reach W6? In the similar way, we can reach this particular W6. So this one, Amol, why 1/2 is there in E total? That is one function which we have taken. Any function we can take. There is different loss functions like mean squared error, mean absolute error, mean absolute percentage error, in root mean squared error. There are a lot of functions we have. There is this one of the loss functions. That's it. All right. And in order to update this particular W5, again we have to backpropagate from E total, E0 to this and to this. So slowly we have to do this one by one. All right. Now, in case if you have to update W1, what are all the connections? So this is one connection, and this is the connection. All right, E01, E02, E total. So this W1's contribution is going like this, right? In the forward pass, W1 contribution is going like this. So in the backward part also, to update this W1, these many connections I have. From E total, I'll go to E1, output of 1, and here, and this part. And again, the second way is E output 2, this particular part, and this particular part. Two things I have to fine tune it. So when the network is, if it is so deeper, I have to do this particular chain part to update this particular W1. All right. So this is what we call chain rule of backpropagation. This would be again complex to understand, but here I've just given all this particular derivations and everything. Just slowly go back and try to understand today. All right, how exactly it is happening. All right. Now here I just E total with respect to E output 1. E total is nothing but 1/2 target minus output of the whole square plus this is what this particular E total is all about. Now with this respect to output of O1, I have to take a partial derivative. So here this term will be becoming 0 because there is no output O1. So if I'm taking a partial derivative of this 1/2, here I'm having 2 multiplied by this 2 will come over here, and target output 1 minus output the same thing. 2 minus 1 multiplied by here target 0. This also I have to take a partial derivative minus 1. I'm getting it plus 0. So after doing this particular cancellation, everything you'll be getting target output 1 minus output of O1. So what is the target output 1? What is expected actually here? Target output 1 0.01. And what is the output that you have got? This is the one. So 0.741. So now you got this particular value. Now you need to go and find out this particular value and this particular value. And finally, you have to take a multiplication. All right, fine, Jyoti. So now see this E total output of 1 we don't know. So now we have to calculate output of 1. What is the output of 1? It's nothing but it is a sigmoid, right? 1 by 1 plus e to the power of minus 6. Now when you take this f of x equal to, if it is 1 by 1 plus e to the power of minus 6, f of x is equal to what? It will be something like this. All right, this is a partial derivative function. Now, because of this, we will be getting f of x 1 minus f of x. And now, what is f of x output over 1 minus output over 1? Now, what is output over that we have calculated 0.7516 and 1 minus, if you do it, 0.18. Now we calculated the second part. Now, what is the third part? Dou net 0.1. So what is dou net 0.1? Net output of W5. So this one. Now we have to take a derivative with respect to W. Now we have reached this particular W5. So now take a W5, take a partial derivative. We got this particular 3 values. Now what need to be done? 3 values need to be multiplied, and now we got it 0.08. Now this is nothing but how much I have to change. So dou E total divided by dou W5 we calculated it, but still we have not updated the weight. All right. So to update the weights with respect to gradient descent approach, we are having on mathematical equation. If you see, now we have to update the weights. To decrease the error, how we have to do is nothing but W5 plus new weight is equal to old weight minus learning rate of multiplied by dou E total divided by dou. This is what this gradient descent equation. My gradient descent equation noted down. Gradient descent equation is equal to, we can say new weight is equal to old weight minus learning rate of dou loss with respect to dou W. All right, we can take it. New dou loss nothing but the loss function with respect to W weight. So that's what this particular point. So new weight is equal to old weight. W5 is nothing but old weight is nothing but 0.4 minus eta is nothing but learning rate. Learning rate is nothing but how fast or how slow we have to go. Usually it will be very low. We can speak about this learning rate later. So here is just a number what we have to initialize. So here I've just given 0.5. 0.5 multiplied by dou E total divided by, this is what something we calculated by multiplying 3 terms, 0.08. Now finally you'll be getting 0.35. So this is the new weight W5. Old weight is 0.4. Now the new weight is 0.35. Similarly, you're going to do this for W6, W7, W8, which is at the first layer. Able to get a picture? All right. So is my voice is not clear to everyone? I think Govind is saying voice is not clear. Is it okay, or is it fine, or is there any disturbance? Let's confirm everyone. Loud and clear. Okay. Then Govind, I think there is an issue from your side. Please check your mic. So other learners are able to hear it properly, Govind. Maybe I think there is some network issues from your side. All right, thanks for confirming, everyone. So this is what your first layer of back propagation. Okay, now we have to again update W1, W2, W3, W4, which is at the first layer. That is even more complex. All right, so see this again, how many paths it is taking it. So now this weights got updated. All right, now I have to update W1, W2, W3, W4. So take this particular slide. I've already given this slide in today's section. Go through it slowly. All right, write it down in pen and paper. Only then you can understand this. And again, this is not something manually we do in practical stages. In case if you wanted to understand the deep math of it, if you're writing it down in pen and paper by spending maybe 3 hours or 4 hours time, you would be good with this particular part. All right. So this is what the connection is all about. Now you update W1, W2, W3, W4. I'm not explaining this. I'm just giving it as an exercise for you to practice, but everything is given in the slide itself. Now new weight is equal to, with respect to gradient descent equation. Now old weight is 0.15. Now the new weight is 0.14. Now we got new weight 0.19, 0.24, 0.29. Now with respect to this new weights, again we are going to forward propagate. All right. So now we got the new weights of W1, W2, W3, W4, and W5, W6, W7, W8. Through back propagation, we got new weights now. Now we take the new weights. Again, we are going to take the same input. We are forward propagating, and again, we are going to compute the loss. Now we have what is a loss function. So in that way, we are going to do it iteratively. Now, finally, we have updated all our weights. When we feed forward the 0.01 and 0.1 inputs originally, the error on the network was 0.29. After the first round of back propagation, the total error is now down to 0.29. So it might see after the first round of back propagation. So here it's not calculated, but it's not shown here, but actually it is 0.29. It might not seem like much, but after repeating this process for 10,000 times, multiple iteration, 10,000 times, the error plummets to 0.0035, which is basically equal to 0. So this is what the point is all about. So the human is able to learn. Let's say you're not able to understand this. Whatever I'm speaking, you're not able to understand. What you would do? Okay, anyway, the situation is you have to understand and you have to give your examination, or this is very much important. So you will watch the recording again and again and again. So that's what this iterations is all about. Learning rate. So with what speed you are learning. The first time maybe slow. Second time you increase the space. Third time even more fast. So learning rate is something important. Portion by portion. What is the batches? How slowly you're taking? How much portion you're taking or learning one day? That is also very much important. So this is why back propagation is very much important. So we are having a loss function, and there are list of loss functions which is available. We are picking one of the loss functions, and then we are back propagating where we are trying to make that loss function to be zero. Got my point, everyone? Even if you miss a single minute, you won't be able to follow the session. Only if you give complete attention to this initial sessions of artificial intelligence. It's not like statistics or Python. So it is something highly advanced topics. Thanks, Shruti. Harsh. All right. Now, as I said, there are different loss functions and wonderful, Chaitanya, great. So let me share the different loss functions, as I said. That's not. Let you just show you the only the terms. Maybe tomorrow we will get into it. Yes, the one. Yep. Great, Chaitanya, wonderful. Govind, can you please share the link of the slide? Govind, I have already prepared it and hand over the slides to the team. You can find the slides in your dashboard. Okay, I know it is a bit painful to understand. So already it's prepared and it's updated in your dashboard. You can take it. Okay. Now see this points to remember. So we have discussed about optimizers, right? So why we need gradient descent? Because to get better weights and biases, and we are having different loss functions. 1/2, that is mean squared error, mean absolute error. In this way, we are having different loss functions. Why we are having different loss functions? Because we are expecting error of zero. So that zero need to happen. So LHS equal to RHS. So what is this LHS equal to RHS? Actually, the output is 50, but my model is predicting 100. So to make Y prediction is equal to Y actual, that is LHS equal to RHS, we are relying on different loss functions. So Y activation functions to trigger a neuron. So there are different loss functions. The optimizers here I mentioned: gradient descent, mini batch gradient descent, stochastic, momentum, Nesterov accelerator gradient, ADA grad, ADA delta, RMS prob, ADAM. List of loss functions, optimizers we have. Different loss functions like cross entropy loss, sigmoid cross entropy, softmax, weighted, Huber loss, L1 loss, L2 loss, hinge loss, different loss functions. And different activation functions are sigmoid activation function, tan H, ReLU, leaky ReLU, exponential linear unit, the parametric ReLU, softmax. These are all the different activation functions we have. Now, tomorrow we will just get into this particular different optimizers, different loss functions, different activation functions. Everything it will take 2 hours to explain. So tomorrow we will get into this. We will understand, and then Friday, we will get into the scripting part where we will combine all these theories. Once we work on the scripting, you will be very confident on your deep learning topic. Okay. All right. Until then, give your best efforts and practice. Today's task is nothing but just practice with pen and paper with respect to the partial derivatives, um, with back propagation, how it is happening and everything. All right. Yes, sir. Even partial derivative is something pretty difficult to understand. Maybe it could have it would have come in your first year or second year engineering. It is a pretty difficult topic. It depends on how our brain is taking. We try to skip it sometimes, and we always know our human brain will always think, where am I going to apply all these things? Why it is needed? So that's what my human brain will always think. That's something obvious and natural. But in this deep learning field, even I have simplified a lot of things. If you're reading research paper and everything, you will feel a lot of things. You will never even get into this path because of its complexity. But trying to make it simplified and delivering it, but try to you also give your best efforts and trying to working out from your side. That in that way we can master more. All right, we can learn it more effectively. That's it. So today we discussed about how exactly biological neuron is working and how exactly researchers came from biological neural network. They got inspired and they constructed artificial neural network. And we discussed about some building blocks and the mathematical side and how exactly uh, back propagation is happening through chain rule of partial derivation. We looked onto it. With that, we are winding up our session now. All right. Let's come back tomorrow, the same time, 7 o'clock, and we can discuss about different optimizers, different loss functions, different activation functions, and then scripting part day after tomorrow. Take care, everyone. See you all by 7 p.m. tomorrow. Bye bye. Yes, Harsh. Bye. Bye, Josie. Take care.